to introduce Professor Joe Vinen, the speaker of this INT seminar. It's my pleasure to do this. I would rather wear a more formal suit for this introduction, but unfortunately my bag was delayed by the airline, so no. So our speaker, Professor William Frank Vinen, he got his PhD from Cambridge in 1956. He then worked at the University of Birmingham as a professor of physics, and he's also named as the appointed professor of physics. Vinen has conducted research that spans a wide range of topics. Thus include superfluidity, superconductivity, two-dimensional systems, and classical quantum turbulence. He's also the one who first discovered and started quantized vortices in superfluidity. He made a lot of important contribution in quantum turbulence. I think his work is very well regarded by the community. And I think many people in the audience actually know Joe very well and interacted with him. So, I think in some sense it's fair to say Joe Vinen is regarded as one of the founders for quantum turbulence research. To myself, I regarded him as sort of advising in this field because we had a lot of interactions in recent years. It's essentially his guidance that I eventually get in this field and then developed my own program. So today he's going to talk about 60 years of quantum turbulence. Let's welcome Joe.
Thank you, Wei. Thank you, Wei, for those flattering comments. And I thank the organizers for asking me to give this rather general talk, which is not at all supposed to be specialized. I wonder what to talk about. But the truth is that I'm probably the only person left who now remembers the time when we didn't know about vortices. So I thought I would at least begin by telling you something of the history of the discovery of quantum vortices and of quantum turbulence. Turbulence was actually discovered in superfluid helium-4 in Cambridge in 1953. 2 to 3 years before, it was mentioned by Feynman. We did not know at that time what the nature of that turbulence was, but we knew that the superfluid component could become turbulent. But exactly how, we didn't know. Now, it's worth remembering that at that time, there were two theories of superfluidity. One was due to Landau, who pointed out that rotation of a fluid at a very low temperature would be difficult because of the quantization of angular momentum. And hence, the only low-lying excitations in a cold liquid would be phonons. If you set the phonons into motion at a low temperature, that motion doesn't carry the whole fluid with it. It only carries a part of the fluid with it. The rest of it is the superfluid component. The moving phonons are the normal fluid component. And of course, the superfluid component, because it can't rotate, ought to be subject to the irritation condition, curl Vs is equal to 0. At the same time, Fritz London suggested that, in fact, superfluidity was somehow associated with Bose condensation. He was thinking, of course, of Bose condensation in an ideal gas, where the condensed particles would be identified with the superfluid and the excited particles with the normal fluid. Again, the superfluid component ought not to rotate. should say that at the time, we experimentalists were pretty skeptical about these theories. Although we did accept that the two-fluid model worked at least to some extent. But I should emphasize that the discovery of quantum turbulence was very much connected with our trying to understand what was really going on in the superfluid. We were certainly not looking for quantum turbulence as such. Well, as I say, both the theories at the time stated that the superfluid component should not rotate. Was this really right? Well, in 1950, Donald Osborne, who was in Cambridge at that time, decided to put this to the test in the simplest possible way. Namely, he put helium into a bucket, rotated the bucket, and to see whether the helium rotated. And of course it did, judging from the shape of the meniscus. So something was wrong. Curl Vs was obviously not equal to naught. But this was not the only problem at that time. According to Landau, the superfluid flow should be frictionless up to very large velocities of order 60 meters per second. In fact, it appeared to break down at much smaller velocities of the order of centimeters per second or even millimeters per second. For example, in a heat flow, such as you have here, a channel with a heater. Heat flow in this channel takes place by a counterflow of the two fluids, the superfluid moving towards the heater, the normal fluid moving away from it. And that's a very efficient way of transferring heat. And according to Landau, the only, unless you exceeded 60 meters per second velocity, the only dissipative process that should limit the thermal conductivity would be the viscosity of the normal fluid. But in fact, Gorter and Melink, who studied this issue around 1949 or so, found that this process appeared to be opposed, this counterflow appeared to be opposed by some mysterious force of mutual friction between the two fluids. But the origin of that force of mutual friction was completely unknown. But there was another puzzle too, and that was that related to the behavior of second sound. Remember, second sound is an antiphase motion of the two fluids. So there's a relative motion between the normal fluid and the superfluid in second sound. But in spite of that fact, in second sound, this mutual friction force, which limits the heat flow in a steady heat current, appears not to act. There was no mutual friction attenuating the propagation of second sound. Well, in 1952, I became a graduate student of Donald Osborne, and Osborne suggested that I should try to study the Gorter-Melink mutual friction force by looking, well, he pointed out, of course, that if you reduce the frequency of the second sound sufficiently, it should go over into a steady heat flow, and therefore the mutual friction force should appear. So I set about trying to make devices which would study second sound at lower frequencies, which was a pretty daft thing to do, actually, and I gave it up fairly quickly. And I turned instead to a much simpler experiment, which was simply to take a thermal conductivity channel of the sort that you've just seen, switch on the heat current at time t equals 0, and see how long the mutual friction force takes to build up. Obviously, it must take a finite time. Indeed, it turned out that it did. And this is one of the very early pictures showing that build-up process. The heat current is switched on here. This is a measure of the temperature difference between the ends of the channel. And you'll see that that temperature difference doesn't build up to its equilibrium value for quite a long time here, which is actually, this is a 50 Hertz timing signal, and this is a time of the order of 1 second. So the mutual friction force built up only very slowly after you had switched on the heat current. What is more, the time it took for this mutual friction to build up depended on the previous history of the helium. If you had put a large heat current in, switched the heat current off, waited only a short time, and then switched it on again, this time turned out to be much, much shorter. Only if you left the helium undisturbed for a long time. Oops. Would you get a long delay time there? And this suggested very strongly to me that what was going on here was that the superfluid component was becoming turbulent. So we ask ourselves a question, and I was working quite closely with Henry Hall at that time. Henry Hall was doing a slightly different experiment where we shared a room in Cambridge at that time. So we wondered whether we had discovered some unknown form of turbulence in the superfluid component, leading in some unknown way to the existence of a mutual friction force. But there was another important step in what we did at that time, and that was to study the propagation of second sound within the heat flow. The original idea of this experiment, I suppose, really was that we wondered whether second sound would propagate at all. We thought perhaps the onset of this mutual friction force was associated with a complete breakdown of the two-fluid model, in which case second sound would not propagate. Well, quickly we found that second sound would propagate in the heat flow, but it was attenuated by an amount that one would expect from a sort of linearized version of the mutual friction that is responsible for this. And this shows here some very early pictures showing the onset of the turbulence of the excess attenuation of second sound. This is the amplitude of second sound resonant signal, and the heat current is switched on here. Nothing happens for quite a long time, then suddenly attenuation sets in as the second sound is attenuated by mutual friction. But this experiment also was very valuable in another respect, because when you switched off the heat current, the attenuation did not immediately disappear. And of course, that is entirely consistent with the idea that what we were looking at was some form of turbulence, because the turbulence that you had generated by means of the heat current would take time to decay after we switched off the heat current. And we looked at the form of this decay. In fact, it had some peculiar features. It had this bump in it. Whoops. Sorry. It had this curious bump in it. The attenuation didn't recover in a monotonic fashion. Sorry. And it's amusing that that bump was not finally explained until about 2 or 3 years ago. So the result of all this was that the damping of second sound became a good way of measuring the turbulent intensity, whatever that turbulence, whatever form that turbulence took. Well, all this we did before we knew anything about quantized vortex lines. But we did know, of course, that theory required that the curl of the superfluid velocity ought to be 0. But perhaps what we were learning, if indeed we were correct in identifying the mutual friction as being due to turbulence. What we had learned perhaps was that the flow of the superfluid need not be rotational, but that if it is rotational, then there is a mutual friction force. Well, the obvious experiment then was to take a bucket of helium, rotate it at a constant angular velocity. We know that that produces the flow of the superfluid for which the curl of the velocity field is non-zero, and see if the second sound is attenuated even in steady rotation. And of course, we found that it did just that. The attenuation was proportional to the angular velocity of rotation. It's amusing that this experiment, when I suggested it, met with a lot of what was almost ridicule. People saying that rotating a macroscopic sample of condensed matter could not change its microscopic properties. Well, they were wrong. But I wonder what would have happened if I had had to put a grant application in to do this work. Probably it would have been turned down. Well, of course, both London and Landau had started to worry about the rotation of the superfluid, as they knew that the superfluid did in fact rotate. And they had started to think about models of superfluidity which would allow the superfluid to rotate. And those models were based basically on the introduction of vortex sheets into the helium. Both London and Landau introduced vortex sheet models, though they were quite rather different in character, but I won't go into that. And so we, Henry Hall and I, began to suspect that what was really happening here was that the rotation of the helium was introducing vortex sheets, and that the interaction of these vortex sheets with the phonons and protons that constitute the normal fluid led to the mutual friction. Well, at that point, which was then about 1955 or so, 1956 perhaps, at that point, we learned of Feynman's famous article in which he introduced the idea that there could be quantized vortex lines in superfluid helium. And of course, that immediately accorded with what we had discovered in a certain sense, because what was happening clearly was that when we rotated our helium, the helium was penetrated by a uniform array of vortex lines, quantized vortex lines, and then the mutual friction would be due to scattering of excitations by these lines. Let me say a little bit about the background theory here. Feynman, of course, in his famous article, based his idea that circulation is quantized on what was really a clever but rather obscure argument based on the examination of the properties of many-body wave function. But the discovery of vortex lines, I think, made people think about what was really going on here, and led eventually to a much better understanding of the way superfluid helium works and of the way in which quantized vortex lines appear as an important component. In a sense, both Landau and London were right. Bose condensation, even in a liquid, leads to the existence of a coherent particle field inside the material, and the quantization of circulation is then an immediate consequence of the requirement that that field be single valued. The establishment of that coherent field, the thing we now call the condensate wave function, is a form of symmetry breaking, of course, and Landau's phonons were, in fact, the Nambu-Goldstone modes connected with that symmetry breaking. And vortex lines are topological defects in the condensate wave function. But given that vortex lines allow superfluid helium to rotate, and given that the Reynolds number, in some sense, in helium is infinite because the viscosity is zero, why is frictionless flow of superfluid possible at all? Well, I will come back to that important question in a moment, but before I do it, let me just say a little bit more about counterflow turbulence. There is counterflow turbulence, shown at the top there, with the tangle of vortex lines being produced by the relative motion of the two fluids. Why does that relative motion produce a vortex tangle? Well, in fact, by a curious argument, the mutual friction force acts in two ways. It can act in such a way as to generate turbulence. It can also act in a way to destroy turbulence. And you can see that by this very simple picture here. Let's suppose we have a vortex ring, which is propagating to the right through a situation where the normal fluid is at rest. Then there is a mutual friction force, which is acting in this direction here. And that mutual friction force via the Magnus effect will cause the ring to shrink. And therefore, the mutual friction force is tending to destroy turbulence. But if we move the normal fluid relative, so that it goes in the opposite direction now, it goes in the same direction as the ring, but at a larger velocity than the ring, then the effect of the mutual friction is to cause the ring to expand. And therefore, in this case, the mutual friction is increasing the amount of vortex line. In other words, it's increasing the amount of turbulence. And this sort of argument led me to introduce an equation here representing the build-up and decay of quantum turbulence, which I thought that equation would last for perhaps a few months, but in fact, people are still arguing the point as to whether it's right or wrong. So let me just emphasize that counterflow turbulence has no classical analog, but nevertheless, it began to play an important role in the study of quantum turbulence. And it's presented us over the years with many problems, and is still presenting us with problems. There are still problems relating to counterflow turbulence that we don't understand. Well, an important step towards the understanding of counterflow turbulence was taken by Klaus Schwarz, of course, who started to introduce the vortex filament model and used computer simulation to see how vortex arrays would develop in the presence of a counterflow velocity. And he assumed that the vortices are move according to classical mechanics. They essentially move with a local superfluid velocity unless there is a force of mutual friction applied, and then that motion is modified according to the Magnus effect. Schwarz assumed that the normal fluid flow was uniform, was laminar and uniform. And he did simulations which showed that, in essence, what we had believed and the basis of the equation that I showed in the previous slide was correct, except for one very important point, and that is that if you're going to have a self-sustaining superfluid turbulence generated by counterflow of the two fluids, then you must allow for reconnections of vortices. And without those reconnections, the turbulence would not be self-supporting. Well, later developments have improved on the Schwartz calculations. Of course, there's still the question of what the normal fluid is doing. Schwartz assumed, and I suppose most of us assumed, that the normal fluid was just flowing in a laminar fashion, and you had the superfluid with this tangle of vortex lines moving relative to this normal fluid. But was that correct? And in fact, I think it was Milot and Berenguer who first suggested that maybe the normal fluid goes turbulent also, and I'll come back to that point a little later. Well, reconnections turn out to be very important, and I think as already been indicated by Carlo, they can't be described except by a microscopic theory. The only microscopic theory we have is the Gross-Pedievsky theory applicable to a weakly interacting Bose gas, but that theory does in fact account for the existence of reconnections, which have been much studied by using the Gross-Pedievsky equation. Well, given that vortices can be created in helium, why is it a superfluid? Why do you ever have frictionless flow? Why doesn't helium has an infinite Reynolds number? Why doesn't laminar flow always break down with the creation of vortices? Well, the answer lies in the fact that the production of a vortex in helium is actually a rather difficult process, because if you imagine, as in the top right-hand corner there, a vortex near a wall being created, it suffers from an interaction with its image in the wall, and that interaction is such as to give rise to a potential hump, which the vortex has to undergo if it is to move away from the wall and develop fully developed turbulence. And it's that very large energy barrier, which of course is in a sense a result of quantization, without quantization it wouldn't be there, is really an important element in understanding superfluidity. Well, given that energy barrier is so large, we then started asking ourselves, well, why do we ever have turbulence? And the answer to that is almost certainly that turbulence, as it is usually seen in helium, is the result of having remnant vortices in the helium left over from previous experiments or passage through the lambda transition. And so real helium contains a few remnant vortices, just as the crystal would contain remnant dislocations. And these remnant vortices act as nucleation sites for the generation of more turbulence of the sort discussed by Schwartz. Intrinsic nucleation is also possible under certain extreme conditions where this barrier at the top of the board there becomes small, for example, close to the lambda transition at very high velocities or in very thin films. And I won't go into it anything more than just saying that. The existence, the fact that the barrier is small in thin films, of course, is responsible for the costless-Thouless transition. I should say that the pinning of vortices, pinning of remnant vortices or vortices in general is not at all well understood, and that's one of the problems which remains for us to try to solve. Well, apart from the work on Schwarz and work by Schwarz and on vortex nucleation, there was actually rather little study made of quantum turbulence until the 1990s or so. And in fact, I will tell you something which was interesting. When I finished the work that I was talking about in Cambridge, I got a university appointment in Cambridge, and I was told by my seniors that I should stop working on helium. Helium was a dead subject, and that was that. And so I did. I did as I was told, and I didn't actually return to helium until after I retired. Well, in the rest of my talk, I'll just say a few words about what time did we start? 10 past or something like that. In the remainder of the talk, I'll just discuss a few topics relating to what I think of as a renaissance of interest in quantum turbulence, which started around 1990, 2000 or so. And I will, for the simplicity, I will focus largely on turbulence at t equals 0, where it's not complicated by the existence of a normal fluid. In classical turbulence, a great deal of effort has been put into understanding what we call homogeneous turbulence, which is generated, as we've heard in the earlier talks, by flow of a classical fluid through a grid. And an immediate question is, what happens if we try to generate homogeneous turbulence by moving a grid through helium, or by doing something equivalent? So let me say something quickly about classical turbulence, classical homogeneous turbulence, which is produced by flow of a fluid through a grid, classical fluid through a grid. Of course, everything depends on the Navier-Stokes equation. But what happens in this particular case, we believe, is summarized by saying that what we do is to create a Richardson cascade. And what happens here is that energy is fed into eddies of a size which is probably ideally is comparable with the mesh of the grid. And we'll assume that we're dealing with a fluid in which the mesh, if you use the mesh of the grid as a length scale, then we are dealing with very high Reynolds numbers. Then, because of the nonlinear character of the Navier-Stokes equation, those large eddies decay to smaller eddies, and then the smaller eddies again, and the interaction is believed to be such that you produce big eddies produce slightly smaller eddies, and then produce slightly smaller eddies again, until you get to eddies which are so small that they're dissipated by viscosity. And associated with that Richardson cascade is the famous Kolmogorov energy spectrum, which describes the way in which the energy varies with wave number, or if you like, with the scale of the turbulence in this cascade process. Yeah, the famous K to the -5/3. In fact, essentially what the Kolmogorov spectrum depends on is that the interactions responsible for this process are local in K space. Well, what happens in the classical? That's what happens in the classical case. Supposing we replace the helium, the classical fluid, by helium at 0 temperature, what happens? Well, let's think about that for a moment. The helium has there's no viscous dissipation in the helium. We can create vortices, and therefore we can create turbulence, and we can polarize those vortices, as, for example, you do when you create a uniformly rotating liquid. And so you can, by polarization of the vortices, you can create big eddies. And so you can create a situation which might well mirror what you've got in the classical case. But of course, you've also got quantized circulation, which means that there is a minimum energy size, if you like, which is sorry. Yeah, which is, you can think of as being the spacing L between the vortex lines. So you might think, perhaps, that if you're looking on a large scale, and if you're a sort of naive experimentalist, then on a large scale, what you see is a system with large numbers of quanta, and systems with large numbers of quanta behave classically. And so therefore, you can come to the conclusion that on large scales, compared with the line spacing, then you might well get a classical or quasi-classical energy cascade with a Kolmogorov spectrum. And there's a lot of experimental evidence that that is indeed the case. But on small scales, of course, that must go wrong. Once the structure of the vortex lines becomes important, and you have a quantum-dominated regime. One of the problems about that quantum-dominated regime is that it apparently doesn't allow any dissipation, or doesn't allow much dissipation. Now remember that the Kolmogorov spectrum exists because you have this cascade which is terminated by dissipation when the eddies become small, when the eddy Reynolds number becomes small. So without dissipation, you could not get a Kolmogorov spectrum. So how on earth do you get a Kolmogorov spectrum in the quantum case if you haven't any mechanism for dissipation? You might say, well, what happens is that this L gets smaller and smaller so that the vortices become closer and closer together. But that doesn't work either, because if L becomes smaller, the velocity, given the quantization condition, gets bigger and bigger. So that doesn't work either. So there's something wrong somewhere. And we need to find some mechanism by which this quantum turbulence can be dissipated. Well, of course, turbulence can be dissipated in ways other than viscosity. I believe that the noise made by an aircraft as it moves over is an example of the fact that turbulence generates sound. And that is a mechanism by which turbulence can lose energy. Now, vortex reconnections are known to emit sound in helium, a little bit of sound. And of course, the vortices in the helium are moving, and that motion will also generate a certain amount of sound. But those two processes, although they emit a certain amount of sound, don't emit anything like as much sound as is necessary to terminate the Kolmogorov spectrum. But reconnections do something else besides make sound. They in fact introduce kinks onto the vortices, and those kinks propagate then as as Kelvin waves, which we've just been hearing about. And so what you expect to get then as a result of reconnections is a continuous generation of Kelvin waves, initially on a fairly on a length scale of the order of the line spacing, but then as the Kelvin waves become higher and higher in amplitude, they start interacting, generating waves of higher and higher frequency, and leading to a process that we call wave turbulence, by which energy is transferred through wave motion, nonlinear wave motion, to higher and higher wave numbers. And we believe that that is one mechanism by which energy can be taken to large enough wave numbers, and at large enough wave numbers, sound emission becomes sufficiently great to terminate the Kolmogorov spectrum. And so what you finish up with is really a situation where you have two cascades. You have a Kolmogorov cascade, which then feeds into a Kelvin wave cascade, and eventually phonons appear at Wilton. At a finite temperature, things are a little bit different, but I won't go into that here. Of course, when one thinks of turbulence, one often thinks of pictures like that, which is a cylinder or sphere moving through a viscous liquid. And that sort of situation has been discussed, has been studied hardly at all in helium. But as Alex Quebec was explaining earlier today, a slightly similar situation, but a more complicated situation where you're dealing with an oscillating object has been subject to a great deal of study. I won't attempt to summarize the results of those experiments, which are quite complicated, but I would like just to mention one experiment involving an oscillating object, namely an oscillating wire, which I think is very pretty and was done by Hideo Yano in Japan. Remember that I said that normally the generation of turbulence depends on the existence of some remnant vortices. What Yano did was to take this vibrating wire, put it into a vessel with a tiny hole, and he filled the vessel with helium through the tiny hole very slowly, and he hoped that with good luck he wouldn't create any vortices. And good luck prevailed, and sometimes he did not create any vortices, and then he showed that you could vibrate that wire with really quite large amplitudes, a meter per second or so, without ever creating any turbulence, showing very clearly the need to have remnant vortices to nucleate quantum turbulence as we normally come across it. Well, of course, superfluidity in helium-3 was discovered in '71, and that led to the possibility of looking for quantum turbulence in superfluid helium, particularly the B phase, which is simpler than the A phase. I won't attempt to say anything about the results that have been very important results that have come out of studies of quantum turbulence in helium-3. I will simply say this, that by studying helium-3, liquid helium-3, superfluid helium-3, you are looking at a superfluid system which is in certain important respects different from the helium-4 system. The normal fluid, in this case, has an extremely high viscosity and cannot become turbulent. The vortex core is somewhat larger and is full of excitations. although the typical size of the vortex core is still typically small compared with the spacing between vortices. And mutual friction force can be much larger than it is in helium-4, especially near TC. So you can study quantum turbulence in different kinds of regime by using helium-3 rather than helium-4. And then helium-3 also admits of the use of certain new techniques. And then, of course, the condensed gases, post-condensed gases. Again, the parameters that one is dealing with are very different. And so you're exploring different aspects of quantum turbulence. Again, I won't say anything, except, of course, that as far as turbulence is concerned, experiments are bound to be limited to rather small sample sizes. Of course, that doesn't stop theoreticians from studying infinite systems. And if they study infinite systems, they're confident that their predictions are unlikely to be tested experimentally. The last, if I may just have a few more minutes, I'd like to, as a last topic, say something about the visualization of turbulence, particularly in helium-4. Most of the time we've been studying turbulence in helium-4, we've been rather like a blind man looking to understand turbulence. Whereas we know, of course, that actually being able to see what turbulent flow looks like has been a vital part of development of our understanding of turbulence from the days of Leonardo da Vinci onwards. And so the question has arisen of, can we somehow visualize what is really going on in quantum turbulence? The earliest attempt to visualize was done by Yamchuk and Packard, who tried uniformly rotating helium and decorating the lines with electrons, and then drawing the electrons off and looking for a pattern on the scintillation screen. And he was able eventually, after a great deal of effort, to see the sort of picture that you see there of rotating helium with the vortices in the rotating helium. But that technique had only rather limited application. But then from about 2007 onwards, people learned how to decorate, well, put into liquid helium suitable tracer particles in the form of micron-sized particles of hydrogen or deuterium. And there are, of course, serious difficulties about interpretation of these results because there are two fluids. And the question is whether a particle is responding to the motion of the normal fluid or whether it responds to the motion of the superfluid or the vortex lines. But nevertheless, other very useful experiments have been done, looking at counterflow, vortex reconnections, Kelvin waves, non-Gaussian velocity PDFs, and grid turbulence. I'd just like to show you one video here. This is liquid helium-4, video taken in Maryland, and those particles that you can see there are particles of solid hydrogen. And if we switch on the heat current, oops, sorry. You'll see, I'll do that again. Sorry, I think I've lost it again. Oh, lost it altogether. What's happened now? Oh. Okay, that's it. There we are. Yes. What is happening there is that if you look closely, some of the particles are moving upwards, some of them are moving downwards. And what is happening there is quite simple. This is the heat flow, and some of the particles are being dragged up by the normal fluid, some are being trapped by the vortices and are moving downwards. So there's the counterflow really showing up. But then another technique was developed. It was originally suggested by Dan McKinsey and has been developed by Wei Guo, using another sort of tracer. The experiment I've talked about there, was using micron-sized particles of hydrogen as tracers. These tracers are metastable triplet state He2 molecules. Now, two atoms of helium do not normally form a bound state. But if you put them into an excited electronic state, then they develop an attraction and you form a molecule. But of course, the electrons are in an excited state, and therefore, unless you're clever about it, that state will decay very rapidly. But you can be clever by imagining that you put the electrons, the excited electron states, into a p state. An S=1 state. And because of the fact that transitions from S=1 to S=0 are forbidden, at least approximately forbidden, the lifetime of the molecule can become very large. And in fact, in this case, it's about 13 seconds or so. And you can see these molecules by a clever technique of fluorescence. Now, these molecules are very small, and as a result, above 1 Kelvin, they do nothing but trace the motion of the normal fluid. Below 1 Kelvin, when there's no normal fluid anyway, they tend to be trapped by vortex lines, so that above 1 Kelvin, you can follow the motion of normal fluid. Below 1 Kelvin, you can follow the motion of the vortex lines. Well, there have been important experiments done recently by Guo and his colleagues, in which he has studied counterflow above 1 Kelvin and using these tracers and looking at what the normal fluid was doing. And remembering that much earlier on in this talk, I raised the question of what normal fluid is doing in counterflow. Well, now we know the answer. The answer is that at low velocities, fairly low velocities, but not so low that you do not have some superfluid turbulence, at low velocities, the normal fluid flow remains laminar, although it may be distorted from a usual parabolic profile appropriate to flow through a channel. But at higher velocities, the thing becomes turbulent. The normal fluid becomes turbulent, and then you can see this turbulence very clearly, and you can measure its properties by means of these tracers. And so now we know what is happening to the normal fluid, and it turns out that in fact, what is really happening above a certain critical velocity is that the normal fluid becomes turbulent. And that is, it's not quite true to say that the normal fluid becomes turbulent. What happens is that both fluids become turbulent on a large scale. So you have this large scale turbulence superimposed on the small scale turbulence, which you associate with the vortex tangle. And understanding that new sort of turbulence in the presence of a counterflow is a really challenging problem, as you know. Okay, well, that is, I've tried to give you some sort of a picture of how quantum turbulence was discovered and a few of the things that have been happening to it, quantum turbulence in the succeeding years. One might ask, well, why study quantum turbulence? People will ask that question, of course, particularly funding agencies. I think it's interesting just to see how quantization affects classical turbulence. And in some cases, you get rather minor modifications, in other cases, major modifications, and you get the appearance of completely new kinds of turbulence. And then one might ask the question of the extent to which, of course, classical turbulence is not well understood. And so can the study of quantum turbulence help? In some ways, the visualization of vortex lines, which amounts to visualization of lines of vorticity, might help. And then there's the question of whether the study of quantum turbulence is related to any other practical applications or to other areas of physics or astronomy, which is, I guess, something we should be addressing at this particular meeting. So there's my summary. And I'll leave you to read that and simply thank you for listening to me.
Any questions?
You mentioned that at high temperatures, the normal fluid will also become turbulent, but that will be a large scale turbulence.
So you mentioned at high temperatures that the normal fluid will also become turbulent.
So,
Well,
determines the large
in the counterflow case I'm talking about, that is a temperature above 1 Kelvin, because otherwise there's no normal fluid there. And in that case, in counterflow, yes, well, you see, okay, let me answer the question. If you study something like homogeneous turbulence flow through a grid, then the two fluids are probably more or less coupled together by mutual friction and behave as a single fluid on large scales. On small scales, of course, that isn't true because the superfluid gets killed, the fluid turbulence gets killed by viscosity. But in counterflow turbulence, where you are forcing the two fluids to move at different velocities, then even there, you can have a situation where both fluids are turbulent.
You mentioned that to create mutual friction between normal and superfluid, you need to nucleate a vortex tangle. Is there experimental control of that nucleation energy? Can you spin it so that it's more or less difficult to create this vortex tangle?
So, sorry, so once more, for the microphone here.
You want me to speak louder?
Yes, please.
You mentioned that you need to nucleate a vortex tangle to generate mutual friction between the normal and the superfluid components.
So you need to generate a vortex tangle to nucleate the mutual friction.
Right.
Well,
Is there experimental control on the energy for nucleation so that you either have easy or difficult?
So is there experimental control on the energy so you can have easy or difficult nucleation?
well, I take it you're referring to the mechanism by which turbulence is generated in counterflow. You can actually study situations which are slightly different from pure counterflow. You can, for example, in pure counterflow, the net mass flow is 0 in the channel. You can still have a counterflow in which there is a net mass flow. And by studying that, you are studying a slightly different system. And that would that is potentially quite interesting and has already been shown to be of some interest.
So I have an historical question.
Yes.
You mentioned Landau and London, but it seems to me that TISA actually.
So you mentioned Landau and London.
Yes.
But it seems that TISA.
TISA has written the first time the.
I should have mentioned TISA. So,
equation,
I'm sorry,
in
yes.
my opinion.
Yes.
And of course, Landau was a bigger.
TISA and London were really one person, yes. I should have mentioned TISA, that's quite right.
No, but you agree. I mean, my question was not a critique. It was just that I think it seems like the contribution of TISA very often is underestimated. Actually.
Yes.
Do you agree? Or?
What?
That the contribution of TISA is underestimated.
I don't actually, to be honest, I don't know, actually. I mean, I think London had a very profound understanding, actually, of helium. I mean, he got it wrong in some ways, in the sense that, of course, an ideal Bose gas is not a superfluid. But he understood in many things about, well, superconductivity and superfluidity, of course. And and what is more, he saw the connection between the two, which was very important. And I might just add one other comment which relates to that comparison of superfluidity and superconductivity. And that was when I was in Cambridge. I mentioned the fact that my colleagues thought my proposed experiment on uniformly rotating helium was silly. It couldn't possibly work. What they had failed to realize was that that experiment was very similar to an experiment on type 2 superconductors. And they were all specialists in superconductivity. They had simply, London understood the connection.
Any other questions? One more.
You mentioned that in order to create vortices, you have to overcome a very large energy barrier.
So in order to create vortices,
Yeah.
you mentioned you have to
Yes.
overcome an energy barrier.
Yes.
Where is the profound, the final reason for this energy barrier?
Well,
What is the final
energy,
reason?
yeah, okay. I thought I had explained that, but I probably didn't explain it very carefully. The point is that the vortex sees an image in the surface, and it's attracted to that image. And so you have to overcome that attraction in order to generate a free vortex. You might ask, well, you could create a little vortex ring in the middle of the helium, but it turns out that unless that ring has a certain size, certain minimum size, you actually, again, you have to overcome a potential barrier.
But in that case, it's just the energy barrier that I have to overcome to
Sorry?
introduce. Is the energy barrier that I have to overcome in order to introduce a roton into the fluid?
Yes.
Or is it something else?
So is the energy barrier what you have to introduce to get a roton, or is it something else? So,
Sorry, I don't understand the question.
so is the energy to put a vortex in the same as putting a roton in, or it's something else?
I think it's something else, actually. Yeah. You can work out what that barrier is, all right, in various circumstances. And you can ask yourself, how might you overcome that barrier? Now, one of the prettiest experiments that's been done has been to look at the nucleation of vorticity by a moving ion. Now, an ion, for the purposes of this talk, is just a sphere which is moving through the helium. And there the vortex, the nucleating vortex is a kind of loop which is attached to the sphere. And that loop, when it's small, has a large positive energy. But as it moves away from the sphere, gets bigger, the energy drops and eventually becomes negative if the sphere is moving. So somehow or other you've got to overcome a barrier. Now, at high temperatures, that barrier can be overcome thermally without too much difficulty. But interestingly enough, if you go to very low temperatures, you still get vortex nucleation, but it occurs by macroscopic quantum tunneling of the vortex through the barrier. And that, I worked out a theory of that, which seems to work reasonably well.
All right. Well, thank you very much for a very nice talk.